Our next speaker is Salah Sukkarieh. Salah is Professor of Robotics and Intelligent Systems at the School of Aerospace, Mechanical and Mechatronic Engineering at the University of Sydney, and he's also a Director of Research and Innovation at the Australian Centre of Field Robotics. I've been through Salah's lab at the university, and for a tech nut like myself, I can tell you that it is a magical wonderland full of robots and drones and machines straight out of a sci-fi movie set. But Salah's job is to take it out of the sci-fi realm and turn it into commercial realities with value propositions for agriculture. So, welcome Salah to the stage.
Well, good morning, everyone. I'll just sit up here. So I was asked to give a talk about robotics and the role in agriculture, and especially on-farm robotics, and that's really where the focus of this talk is all about. There's a web link there for all the videos that I'm going to show here if you want to look at those videos and download them from there. It may seem like it's a future technology of some form, maybe 10 years, 20 years away. We'll see how it goes within the agriculture space. But what I do want to start with is by saying that Australia actually leads the world when it comes to not only the R&D of what we call field robotics or outdoor robotics, but also the operationalisation of those robots and the commercialisation of those robots. We have, over the last 20 years, worked with a number of different companies in this space. So Patrick's Theodores, if you drive 10 minutes down here, you'll see a fully autonomous birthing operation. All that technology was developed at the university, fed out into Patrick's. Over the last 10 years, we've been working with Rio Tinto in their Mine of the Future program and developing not only autonomous trucks, but a complete autonomous operations. Qantas, we do a lot of work in terms of their autonomous decision-making and flight planning systems that they go through, and also within defence and underwater ecology. So that's just really to paint a picture that Australia does do a lot in this space, does a lot in terms of not just building the field robotic systems, but putting them into operation and making them work in whatever way. I wanted to kind of just show you where robotics sits in this whole space, because we have been talking probably around the first three elements there: sensing, data analytics, and decision software system supports. Once you start going to the next realm, which is real-time awareness, so not collecting data and then processing it and getting results 5 hours, 10 hours later, but actually start doing it in real time, that's when robotics really starts to kick in. Then you start to get mobile sensors that can do things of different forms. You can then move into automated tasks of some form, and then completely into that farming operation space. But it's not to say that that's what all robotics is. So what happens is, roboticists, we want to make these systems work in real time on the farm, for example. And in doing that, we develop a lot of the algorithms, and those algorithms can get then fed back into the data analytics and decision software support tools as well. So that's that kind of feedback that we see. What we have learned from other industries and what we want to maintain in this industry, we hear a lot about robotics and how we're going to have completely autonomous farms. That's probably not the case, because we haven't seen autonomous of anything yet at the moment now with any human interaction of some form. So really what the focus is how do you build these robotic systems and solutions and have them as support systems and support tools that operate in real time on the farm for the grower. So I'm just going to go through some examples of what we've done and where some of the future directions are going in those spaces, and just so that you can see and get a feel for it all. The first one's in tree crops, and that was the first area that we really tried to tackle with ground robotics. And really what the industry was interested in was, how do we improve crop intelligence? So how do we know more about our crop down to the individual tree level, down to the individual fruit or nut? And that's really what they were interested in. We saw previously an image about what was going on in MIT with the indoor type of vegetable growing, and where every vegetable might have its own IP address. It's very similar context, but now it's doing it outdoors. Outdoors it's a lot harder. Wind, leaves move, fruit move, illumination from the sun. There's a whole bunch of different conditions, dust, etc., that complicates it all. And I'll just show you how we tried to tackle this problem, so you get some sort of idea of where we tried to target it so that we get the low-hanging fruit, for the grower in some way, and so that the robotics kind of eases its way into the operation, as opposed to thinking that we're going to have a robot that does everything straight away. This is just a time sequence, right? And you've got the season boundary, and we're looking at the apple process here. And we spoke to apple growers, and we asked them, what do you do during the apple process through that apple season, right? And so you get the standard process that you're going through, pre-pruning all the way through to packing. And then we said, within each one of those elements, what do you actually do specifically, right? So then you get this whole list of activity that comes out of that. And then for each one of those elements, can you tell me something about the amount of information that you have for that task and what impact that has on the operation itself? So those little L's and H's and H's you see are those variables. So this one here, for example, they have high information and it has a high impact on their operation, so that's great. But there are elements there where there's low amounts of information but has a high impact on their operations. And all those things that I have in yellow there have been highlighted as in, probably one way to look at it is where is the greatest risk in terms of the information flow. Okay, and that's what we just try to sit down with, and that's where sensing, data analytics, but also the mobile version of those, the robotics version of those will have a high impact. So we had a robot which was called Shrimp, and there's two robots, they're called Mantis Shrimp, and anyone who knows anything about those animals that live under the water, the shrimp versions, they've got 16 different spectral bands, and so they see the world in a very different way, and so that's really why we call these bots that. But we had these bots before, and the tree crop industry was saying, you know, can you start to use them in some way to look at tree crop intelligence? So we mounted this sensor tree on top of it with a collection of sensors on board, everything from vision and laser and radar, and basically this robot will just go up and down the rows and start collecting information, and there's enough computing power on board that robot that it analyzes everything in real time. Okay, so it's not upgrading into the space. But this is what the robot sees. It sees a collection of different types of modal spectral frequencies in different ways, everything from hyperspectral, infrared, thermal, and it draws all that. What you see is a collection of trees with different responses, but from a robot's perspective, again, they're all just ones and zeros. So we have to go through a series of algorithms now to try and train the robot into understanding what a tree is, to train the robot to understand what a fruit or a nut is and a flower is, and so forth. And so you go through what you've heard before, which is this data analytics or machine learning and deep learning. There's optimization algorithms. There's a collection of algorithms that we work with. You collect all this data. You have to align all the data together in some form, right? So that's the important element that you have up here. And then you see this dashed line, and there's two things that happen. There's this pre-set of activity and the post-activity. The pre-activity is a collection of machine learning algorithms. Is really what it comes down to. You're basically writing some algorithms, optimization algorithms, machine learning algorithms, and you're training these algorithms to detect certain things. And what you'll do is you throw at these algorithms, for example, red, green and blue from the vision sensor, plus some infrared, plus some hyperspectral sensor signals. And you go to this algorithm and you say, look, here's an apple, here's an apple, here's an apple, here's an apple. And it kind of looks at all the data and it says, okay, I kind of see what an apple is, etc. And then you might throw it at a leaf and you say, this is not an apple, this is not an apple, this is not an apple. Very much like what you do for a kid, and you kind of train these algorithms up. And once you train them, you throw then a new set of data, and then you start to see whether those algorithms are working properly or not. If they are, then they go on board the robot, and that's what happens below the hash line. So what you get is this robot that can go up and down the rows. It's not an easy task because these tree rows are quite high and you get GPS signal attenuation, so you've got to look at different types of technologies that will actually allow the robot to go up and down the rows in a nice, clean fashion. And it's collecting information about the trees, and we've got a series of algorithms that kind of segment out what the tree is and then start to look at the different types of objects in there. This is important to, right at the end when I look at a bit of the conclusion, the architecture of the plant is going to be very important when we start to think about the future of autonomous farms or robots on the farms, and then I'll talk about right at the end. So this is what you kind of get, which is on the left here is the vision data that you will see, and on the right is the robot counting every single flower and detecting every flower as it's going down the row in real time. Okay, so it's doing that just before they go through the pollination process. And then just before harvesting, we've done the same thing. You go down the row, the robot sees what you see is on the left and what the robot sees is on the right, and all the red circles is it detecting all the apples in real time as it's going down the row. And that becomes an important element. So now you've got an ability to be able to detect all the flowers. I can go down to the individual tree, say how many flowers. I can even draw a density map and say where are the flowers on that tree. And I can do the same thing with the apples as well. I'll give you an example of where this worked on a really good farmer, Melbourne, apple grower, did a lot of our trials on his farm. We showed him a flower density map. The flower density map was very uniform. The apple grower predicted about 80 tonnes of apples we're going to get at the end of the year. When we went through harvesting, we had to force him and the workers to count every apple before they harvested, right? Because we had to do a ground truth in that process. We got about 95% accuracy in terms of being able to detect individual apples. When you looked across the paddock, there was a drop in the amount of yield of the apples from east to west. And as soon as we showed that to the grower knew straight away what it was, and that was there wasn't enough pollination trees down on the other side. So for the last 10 years, growing this paddock, getting good estimates about what he predicted the future harvest would be, and yet there was about a 30% drop in yield down at the other end. And that was the ability to be able to go down to that individual row and individual tree. In the first few years of these trials, we did a lot of work in apples and almonds. Very different tree architecture here, so it's a much more complex problem. Robots going down autonomously up and down the rows. The laser unit's able to detect each individual tree as it's going down. The robot can then, as it's pulling out each tree information from the laser data, is then looking at its vision database, and it's saying, where is this tree, where is this tree? So it can start to pull out each individual tree as it's going through. A grower can come along now and just click on any one of those trees on their map and they can get a latest image. But the robot in real time also, what it's trying to do is detect individual flowers, as you'll see here, and it's trying to estimate how many flowers there are on that tree. And likewise, just before harvesting, again, we can go through and detect each individual almond. And this is just a visual description for you, but from the robot's perspective, it's counted the number of almonds on that tree and so forth. And then you can overlay that onto something like Google Earth, and the farmer can come along and click on any one of these images that you see on any one of the trees and get the latest vision data or vision result from that process. Currently, we've extended out the trials. We've got another 3-year funding cycle to look through the tropical fruit, so mangoes, bananas, macadamia nuts as well in that. And there's been already some really good results on that. And that's linking satellite data with the ground robotics data. So you get the coarse resolution and the high resolution, but you get a 2D plane with the vertical plane information. And that gives you a much more comprehensive picture of what's going on. Just being roboticists, and we've heard about hackers and so forth, we wanted to kind of trial out different things, so we took one of our other robots out to a farm and thought, what would happen if we did something like this? And we were just having a bit of fun. This is a wheeled, legged robot. It can just kind of move up and down between the different tree rows, and it's got a collection of sensors on board. And we did a few things like put a sensor on the robot arm. It can kind of zoom in and under a tree and so forth, right, and go underneath. And we put a little sensor on board. You can see what the sensor's seeing it as it kind of lifts up its leg and repositions itself to maintain stability. And the growers are going, oh, this is great. This is for pest detection, looking at the trunk and so forth. Some of the work that we're looking at now is getting closer to what happens when you want to individually spray fruit or get to the point of selective harvesting. I've detected that this type of fruit is ripe and I want to start harvesting. It's a robotic arm with a sensor on board, and as you know, you get a lot of occlusion, apples around leaves and so forth. And what you do as a human is you reposition your head to kind of count how many apples there might be in a bunch on a tree. And the same thing is happening here. This is information sampling, a sensor looking at a tree, and it's looking at the information, and it's then trying to determine what is the next best position to be able to move the sensor so that you get a better picture of what's going on in that space. And that's some of the future research that's starting to feed through. So row crops is the next industry, and this is really looking not just at the crop intelligence, but also the robotics as well. We got some funding from the vegetable industry to look at not just doing the same thing, but building and rethinking what robotics might look like on the farm. This is Ladybird, and we designed it straight away from scratch to look at solar electric and see what we could push the boundaries on in that space. It's a modular unit, so we can lift up the wings, so that you look at different height crops. It's got no drive shaft. Each one of those drive wheels is its own entity, so we can adjust the width quite easily. And it's got a little robotic arm that we can start to play around with and do various things on it. And it was built at all, we designed it in about 3 months, then kind of focused on the wing design because we wanted that to look really good, which took us another 3 months. And then we built it within a week, and then it was out from there. The bot can operate for about 10 hours on a day like you see there. So it's got enough capability both in the battery source and the electric to be able to operate for about 10 hours. But what it's doing is it's going up and down the rows. All we have to do is click the width of the row, and this is what the paddock boundaries are, and the robot will go automatically up and down. And what the robot can do is, as it's going up and down, it's stitching all this imagery, mainly for the grower. This is purely for the grower's exercise. The robot, again, doesn't care. The robot just sees ones and zeros. But what the robot's interested in is how can it detect the difference between a crop and a weed in this particular case. So it's being able to detect the difference between those two. And we use that little robotic arm to try and test out, once we've detected a weed, can we automatically start to shoot each individual weed. So this is a trial where we're just detecting anything that's green. You can kind of see it, they're just spraying what it needs to spray on each individual little element there. Our goal was, how can we reduce herbicide? That was the big focus, right? So one step is to come along and say, precision target, spray, and that's it. You can see that the next generation of this would be, if I look at a crop and I'm looking at crop variability, can I just spray enough of the fertilizer, for example, on that crop? But we've also, if you look at the website, you've also seen some mechanical hose. We've decided to put a little hoe on that robotic arm, and it can just kind of hoe out all the stuff. It's completely herbicide-free. But we're still a while off. The veg industry then said, can you build a pre-production bot, so something that that maybe can get onto a farm, and that's really where Ripper came along. You know, again, we're using all the acronyms here, and I'll tell you what the acronym is later for that, but it's Ripper. And it's about half the weight of Ladybird. It can operate for, well, we did a trial, actually, I'm going to show it here. We did a long endurance trial just about 6 weeks ago in that space. It started from 5:30 in the morning, ran for 22 hours non-stop, right, through the whole day. I'll just jump through because it's in the interest of time. Right, ran through, this is at night, at about 3 o'clock in the morning, it came to a halt in the middle of the paddock and just stopped there because of the lower power system. And then at about 10 o'clock the following morning it recharged and off it went on again. And it was just doing that. And that was really us just demonstrating continuous operation of a solar electric bot going up and down the rows. And what it was doing is it simultaneously was detecting, and with the same mechanism I showed you before, being able to detect each individual crop in real time and being able to spray on that. This is just water for now. This is just part of our process of going through there and just being able to do, you know, trying to see what that next level of technology might be. So the future funding in that space now over the next few years is really looking at being able to make the bot even more intelligent. So this is about the on-farm autonomy. This is about making decisions on the robot in real time. So you can see the vegetables in different ways using near-infrared, hyperspectral and so forth. This is the robot collecting the data and being able to look at vigour or yield in this particular case, and being able to do this in real time. The red here being high, the blue being low. And so what you can imagine, what we're trying to do now over the next few years is if you can detect that, can you spray what you need to spray on that particular crop and reduce the amount of crop variability that's going on there. And being roboticists, we work very much in the probabilistic domain, so we like everything being uncertain, stochastic. We like modelling it around that. And so what the robot's really doing is it's estimating and looking at growth and yield, and then based on models, biological, biophysical models, as well as weather and so forth, what the predicted future might look like, what a really good case would look like, and what a poor case would look like. And I've just broken it down to 3 elements here. You can imagine there are a million futures in there. It's just probabilistic, and it's just throwing out potential futures. And from that, there has to be a decision. But the decision is probably most likely not with the robot itself, but it's a grower-robot kind of scenario. This is the one that I think will most likely happen, and the robot then goes out there and does the task that it needs to do. And the final area that I want to talk about is the work that we've been doing in grazing livestock. We started off a lot, and we spoke, you heard this in the previous one, a lot to do with using drones and in weed detection. This was a project that we had back in 2007, funded out of MLA to look at weed detection over large properties. And this is not about flying a drone and collecting data and then passing it on to a human, as you might know from other projects. What we really were trying to do here was how do we collect that data and again do the same thing, pass it through machine learning algorithms. So here we can stitch a 3D terrain map. These are us detecting weeds and teaching the machine learning algorithms about the weeds. And then as the aircraft is flying, you can detect individual trees, put bounding boxes around the trees, determine the size of the trees as well. And then it passes it through the machine learning algorithms. And as it goes through the machine learning algorithms, it's detecting the different colours here are representing the algorithm detecting the difference between a prickly acacia, for example, and an eucalypt tree. And then what you can do is you can locate where all the weeds are autonomously, find the shortest path between it, and part of that project was sending out an autonomous helicopter, a small one with a granular herbicide, and just dispensing granular herbicide on each one of those weeds. We just finished a project now with the Department of Agriculture looking at large-scale operations. This platform here that we looked at here, it has a 7-hour duration. It's battery-operated, collect the sensory data, and it's doing it over large operations. And we've been doing things such as detecting different types of weeds autonomously along the place. So the data are fusion algorithms. This is an example of one of the farms. It's actually a university farm, which tells you how bad it is, right? In Serrated Tussock, that's going all over there, right? And being able to autonomously do that. Part of that is how do you use drones, but also part of that is the information management system that you get through there. And obviously, and a lot of the work that we're trying to look at is how do we improve pasture quality, but also how do we look at animal monitoring and monitoring the health of animals. And that was predominantly the drive here. So then we also started to look at ground robotics. We took shrimp, which I showed you before, and this is it herding. This is just us, again, roboticists, just having a lot of fun and just wanting to know what robots can do. But the important part is this part. The robots can identify individual animals, can identify where they're eating, understanding how they're moving, whether they're sick or not. That's part of the future research that we want to be able to look at. What's the pasture quality at that particular point where they're eating, because that affects milk quality and how we're going from there. We took that robot that I showed you before, Ripper, out to a landscape scenario and tried to test it out. The reason why is we wanted to see what the limitations of that type of robot is. We've got some funding out of that industry to be able to, in the next month you'll see a new robot coming out specifically for landscape scenarios. It has to be a lot more flexible and agile and be able to work in that environment. And another area that we've worked on is how do we use drones for tracking animals, so little radio tags and being able to detect them from kilometres away because you're up in the air, and being able to detect and understand herd motion, for example. So that's all on the industry side. Again, coming from a university, the thing that we're seeing, well, the thing that I'm seeing a lot is the gap between, and we've talked about this before, the agronomist, the farmer, the computer scientist, and how they're all coming together. So we've got a little program in there that's starting to look at how do we look at rural STEM education. So STEM is science, technology, engineering and maths, and how we feed that into the rural schools, basically. So we built this robot. This is called Wallabot, right? It was originally called Kangabot because it was a lot bigger, but we kind of had to make it smaller. So all the smarts are in the wheels here. So there is all the electronics and the drive modules and et cetera in the wheels. And basically what that means is I can actually adjust the wheel separation distance. So really what we've got is a two-wheel tractor, okay, in that space. It's a very simple robot and very easy to use. And what we've done is we've connected up the system to some coding algorithms. And what you'll see here is a description of some code that's been written for the bot. And I'll kind of explain it a little bit here. This is a graphical interface. So just like kids playing a game and they can play around with the robot and so forth. But if you jump ahead a little bit, what you'll see is this code that's opening up here, which is what we call functional code. And we may not know, but the kids probably know now, but there's a thing called the hour of code. Lots of schools are actually doing it now. It's using a concept called Scratch, which is this code that you see on the right. And basically, it's not low-level code, it's a higher-level code. Move the robot forward, turn right 85 degrees, go for another 5 minutes, turn left. And it's actually teaching kids how to code. So they're actually coming along and they're putting structure to it and they're actually being able to play around and code with it. So over the next 6 months, there's a number of schools already that this bot will be going to. And really what we're doing is training the next generation, high school children, about how to control robots and use robots on their farms and use them as 2D tractors and so forth, and be able to use that coding relationship with the mechatronics relationship and hopefully get the next generation through. So my last slide is just conclusions. I asked to give a bit of conclusion about where I think it's going. I think so. Robots and intelligent systems, if I see it in all the other industries that we've worked with, they're coming. They're eventually going to come into the agriculture sector and be there. And so I don't really think it's about whether robots are coming, but is whether my future operation is ready for that type of robotic technology to come through. And so the future about operations and intelligence, we've got to rethink the architecture of farms. We've got to rethink the business models as well, because that all has an impact on it. As an example, the apple orchard that I showed you before, which was on trellis, is ready for automation straight away, okay? Because of the fact it's on a trellis, all the fruit and the flowers are on one side. The almond orchard's a lot harder to do. Okay, so being able to rethink ahead and start, and we've had this discussion with a number of growers now about they're going to start replanting large acres. So when they're starting to replant, what does that future farm look like? What should I do now in order to start planting from it? So that's something that we need to look at. 24/7 monitor operations is also going to have a big impact as well. You've heard a lot of this already before. Standards will become very relevant very quickly, and that to me is a big thing. I think we need to go through that straight away and start to look at that, because we want to be able to do plug and play, and that becomes a big element in that space. But the way technology is moving, expect to see some rapid hardware and software changes happening. Okay, it's not going to be as slow as it was before. I know we've said ag has been very slow, but things are picking up very, very quickly, and we're going to see lots of changes very quickly. And finally, I mean, I just came back from an agri-tech conference in the US. It's huge, right, when you think about it over there in terms of data analytics and robotics and so forth. The startups, there's so many over there. They're starting here. We're already hearing about all the different startups, people, everything from drones and ground robots and data analytics and so forth that are coming through there. We've heard just in the previous talk the changes that this is going to happen to the food supply chain. If I can identify individual fruit continuously over the life cycle of it growing, or the animal, or whatever it might be, it's going to change the way I understand what's happening on the farm, and that's going to change the whole supply chain process after it as well. And finally, the knowledge transfer, which I think is going to be important. There's going to come a time, the way we see it, is that you're going to have the robots on there and doing whatever they're going to do, and all people are going to be really doing is writing apps the same way that you'd be writing apps for your iPad. Okay, and writing apps to do particular things, and those apps are going to be shared all across the world, and that knowledge transfer is going to be important as well. How that fits within the big organisational profiles that we see before, ahead of us, like tractor companies talking to seeding companies and so forth, I don't know, but that's another area that we've seen that kind of disruption in other industries, and we'll see it, I think, in this one as well. So thank you for your time.